Now in our acceleration video, we focused a lot on the velocity time graph that we ended up deriving, and we ended up finding that looking at just the basic idea of acceleration of a car, initial velocity is 0, and one of the things we realized was that as we accelerate, we actually cover more and more and more ground with each passing second there. And we graphed that out in a position time graph, and then we said, that's a nice graph, let's move on to the velocity time graph, and we found slope was acceleration and area under was the displacement. Well, in this video, I want to come back and I want to look at specifically that position time graph now. So the position is actually increasing in a quadratic manner as time ticks on, meaning that we cover more and more ground. In the first second, we only cover 1 meter, but in the second we covered 3 meters, and in the third second, we covered 5 meters, so forth and so on. And so whenever we graph that out, we get this nice curve, a quadratic, and it actually follows what we call a kinematic equation. There are 4 kinematic equations. Right now, we will be studying 2, and in this video, we'll be studying the first one. So the kinematic equation we're going to be using today, S equals ut plus 1/2 at squared, where s is the displacement, not the distance traveled. That will become important in an example problem. U is the initial velocity, a is the acceleration, and t is the time. Notice that this kinematic does not have final velocity in it. This is a good kinematic equation to choose and to use to solve a problem if your variable bank, if the problem and then your variable bank doesn't have anything about initial velocity. Now, this kinematic can be applied to solve for any 4 of these variables for something occurring in the x-axis, the left and right, kind of like this car accelerating forward. But it also can be applied in what we call the y-axis, like over here, where maybe we drop a ball, and the exact same behavior occurs. In the first second, we go a little ways. In the second, we go even further. In the third second, we go even further because we are accelerating. See, there's an acceleration downwards. Specifically, it's the acceleration of gravity. Negative 9.81 meters per second squared is the acceleration of gravity, assuming that we call down negative and up positive. It's going to be very important that we choose a coordinate system in all of these problems. Now make sure to write down in your notebook the acceleration of gravity. It is a constant when near the Earth's surface, negative 9.81 meters per second squared. And in a freefall problem, you actually don't have to be told the acceleration because you already know it. Let's put an AG maybe on that to make sure that we know that it's the acceleration of gravity. If it's something that is falling or is not having a force applied and it's moving up and down only in the y-axis, gravity is pulling it down negative 9.81 meters per second squared. All right, let's do a few example problems now. Number 1, a certain car has a maximum acceleration of 4.1 meters per second squared. So it looks like the car is going to floor it out of this red light. The car accelerates from rest at a red light for 5.5 seconds. Calculate how far, this is S equals question mark there, the car travels while accelerating. So it looks like I have an A, looks like I have a T, and I missed something here. The car accelerates from rest, meaning the initial velocity is 0. So as you can see, I've already ended up drawing a picture. Now let's make a variable bank. All right, looking at my variable bank, I have an acceleration problem. This isn't constant velocity. Notice it even gives us an acceleration. And it doesn't have final velocity in my variable bank, meaning that my position kinematic is perfect to use here. So let's go ahead and rewrite the equation. Next step, after we rewrite the equation, we substitute in. S is what I'm looking for. I'm going to leave that as my variable S. U is 0 times a T of 5.5 plus 1/2 the acceleration 4.1 times my time squared, 5.5 squared. Sometimes students will get confused with the unit of acceleration, noticing that it is meters per second squared and think that means you square the 4.1. That's not true. That's squared on the seconds as part of the unit. It's just part of the unit there. Now we're going to end up working our algebra over here, but there actually isn't any algebra to work. S is already on the other side, so I can go ahead and plug this into my calculator. Now 0 times anything is 0. When multiplying these terms together, I come out with about 62 meters, and 0 plus approximately 62 meters turns out to be a displacement of 62 meters whenever we round for our two significant figures that we have. Two sig figs here, two sig figs here, so round for two significant figures. Now, I neglected in this problem, very poor job on my part, to point out which way I was declaring positive and negative. I'm declaring to the right positive and to the left negative here just because that makes my life a lot easier. That way my acceleration is going to the right, positive, and so my displacement's going to go to the right, positive as well. You can get away, kind of, sort of, with not declaring positive and negative as long as we don't change directions at any point in time, and so everything you're declaring is positive. All right, let's look at a free fall problem here. I have a student dropping a ball from the school building. The school building is 8.9 meters tall. That's how far the ball is going to fall, my displacement S above the ground. Calculate the time t equals question mark, the ball falls before hitting the ground. So I sketch out a picture, kind of like this over here, and then I go ahead and start making my variable bank. Now, a few things to notice. I made my displacement negative because I'm going to declare down to be negative and up to be positive. I could reverse that, but for now, if this whole which way you declare positive and negative is confusing, just down negative, up positive. Now, there are only currently two terms in my variable bank, but there are two other things that are implied. First, the student drops a ball. That means that my initial velocity here is going to be 0. Also, since the ball's in free fall, I know the acceleration. It's the acceleration of gravity, negative 9.81 meters per second squared. A common thing that you will have happening in these free fall problems is you will not be told the acceleration. You're supposed to know that, and you also have to look for key terms. Drops means that your initial velocity is going to end up 0. Now, this variable bank fits perfectly for my position kinematic also. I know it's accelerating. It's a free fall problem, and it doesn't have final velocity. So now I've rewritten the equation, and now I'm going to go ahead and substitute in, making sure that I also plug in what was negative. Displacement was negative because it was going down, and I said down was negative, and the acceleration was negative because, well, gravity kind of points downwards. All right, so I've substituted in, now leaving my t's as t's because that's the unknown variable that I'm solving for, and I'm going to go ahead and begin to solve the algebra. But before I even start that, I can recognize that 0 times t here in this middle term is just 0, and so I can completely get rid of that. 0 plus 1 half 9.81 times t squared. The zeros just completely go away. So I reduce down on the next line, and then I'm going to multiply 1 half times 9.81. 1 half times negative 9.81 turns out to be negative 4.905. Now I have to do my first step of algebra. Divide the negative 4.905 over to the other side. That leaves me 1.814 equals t squared. My last step, how do you undo a square? With a square root. So I'm going to square root both sides so that the square root and the t and the square on the t ends up canceling out, giving me a final time here of 1.3 seconds. Positive there because time is always positive. Just a note here, if you ended up forgetting a negative, maybe you dropped a negative off the 9.81 as I almost did there coming from this step here down, you'll end up having a negative inside your square root, and your calculator will spit back an error at you or an imaginary number, and obviously we don't want imaginary numbers for our time. That just means that you dropped a negative somewhere. Go back and check your positives and negatives. All right, one last problem that I want us to look at here. I want us to look at number 3, where we're actually going to throw the ball up while it's accelerating down. So another student, same school building, decides to throw the ball upwards, straight up off the school. Here's my displacement again. It's still S there, still going down 8.9 meters. Instead of dropping it, the student throws it straight up. Calculate how fast the student threw the ball. If it hit the ground, here's a time. T seconds later. Now in this problem, many students end up getting a little worried about the S still being negative 8.9 meters per second squared. Remember, S is the displacement. how far the ball travels direct line distance from start to end. Well, yes, the distance that the ball travels comes up and then goes back down, but the displacement from the start to the end is the direct line distance, straight down. It travels negative 8.9 meters, negative because we're going down. And even though we threw the ball up, gravity still points downwards the entire time. So gravity is still AG pointing down here, negative 9.81 meters per second squared. Gravity doesn't switch and point upwards just because you throw something upwards. In fact, the entire reason that it slows down, it's decelerating, is the acceleration of gravity is pointing the opposite direction, the motion of the ball. So I've done my variable bank now. This again, of course, is perfect for a position kinematic, no final velocity, and it's an acceleration problem. So let's rewrite the equation and substitute in. So I substitute into my equation, leaving the u blank, because that's what I'm looking for. I incorrectly wrote a second ago u equals 0. I apologize for that. We're calculating how fast the student threw the ball. That's going to be the initial velocity. How fast is it going here in the beginning whenever the student threw it? I put in my displacement, negative 8.9, my acceleration, negative 9.81, and then I begin to simply work the algebra. First thing is I can shove this entire term into my calculator. All right, now I'm on to my first algebraic step. I need to add the 17.7 over to the other side. Notice that it is negative 17.7. That's why I'm going to add the 17.7. Do, undo, I'm doing the opposite of what's here. So add over 17.7. And I end up with 8.8 equals u times 1.9 seconds. So I'm going to divide both sides now by 1.9 and come out with my answer. And it looks like the kid threw the ball upwards because the answer turns out positive here, right? Positive 8.8 divided by positive 1.9, so that gives me a positive 4.6. Looks like the kid threw the ball upwards at 4.6 meters per second. If you're trying to trace the positives and negatives, notice that whenever I had a negative 17 because of my negative acceleration of gravity, so then I added it over negative 8.9 plus the positive 17.7 because it was added over, results in my positive number here, giving me a positive initial velocity, just like I expected, right? We said the ball was thrown upwards.